Okay, so maybe it's time for me to start. So I want to say a few things about what happened last time. Last time we were particularly concerned with, let me see, have I a mouse? Yeah, okay, we were particularly concerned with this figure here, which is got by rotating 3 cubes. Oh, sorry. And I introduced the spin axiom and the Cauchy-Specker paradox. This configuration, the Paris configuration, is just that thing I had last time with 9 points on the face of each face of a cube and so on. And that's one of 3 axioms, and that's one of the safe ones. So let me talk about that axiom. That's the spin axiom. That's the one where if you ask a certain kind of particle what its spin is, it was more precisely defined last time in 3 different directions, 3 mutually perpendicular directions. It always gives 2 ones and a 0. That's the 101 rule, or the spin axiom. And the intriguing thing about that is that it already shows, by the Cauchy-Specker paradox, that what we call the spin in a given direction, strictly speaking the squared component of spin in a given direction, doesn't exist before you measure it. Well, no, not quite. It doesn't exist just as a function of direction before you measure it. So there is no way of assigning to each direction, and in fact to each of these 33 directions, something called the squared component of spin. Because if there were, then it would have to satisfy this rule, and the Paris configuration can't be colored with 1s and 0s so as to satisfy that rule. Now, the spin axiom is a checkable axiom. It's operational, is this standard slang. If you don't believe it, and you're in a suitably equipped laboratory, then you can take a particle, measure it in any 3 orthogonal directions you like, and you'll always get 2 1s and a 0. And after you've done that for thousands and thousands of particles, you'll become convinced that the spin axiom is true. Now, the next axiom, in the version of the paper that we first produced, it was called the fin axiom. So let me just say 101 rule. This was called the fin axiom, and it said information can't be transmitted. I'm going to stop writing on this board after a time, but I want to do it here at more than the speed of the... Well, let me just say fast. Where that's precisely defined and so on. Now, this axiom does not have that operational property. It really doesn't. So you've got to sort of understand why one should believe it to be true. I don't want you to take anything on authority, even Einstein's authority. So that's what today's lecture is going to be about, really. Why should we believe it? And then there's also another axiom called the twin axiom. So let me just say that each of these is operational. In other words, you can convince yourself, operationally definable. You can convince yourself by a sequence of experiments that it's true. Each of them says that something or other implies something else, and you can take lots and lots of cases in which the hypothesis is true, test it and see if the conclusion is true, And it is. So these don't present any problem of understanding what on earth is meant by it. Which is rather peculiar, because these depend on quantum mechanics for their justification, really. I mean, this is why we came to believe that they might be true, so to speak. And quantum mechanics is very funny stuff, you know. It's very hard to understand. And so you might sort of think, oh, anything depending on quantum mechanics is going to be very dubious. But that's not true. These two particular things, we selected them very carefully. They don't have a dubious quality at all. You don't have to believe quantum mechanics. You just have to be capable of doing the tests. Okay. Now, later on, we replaced this spin axiom, not the spin axiom, sorry, the fin axiom. Fin stands for finite speed, replaced by min, which is a more precise axiom, and it doesn't give rise to any troubles. Originally, we sort of thought it's okay to quote this thing about information not being transmissible at more than a certain speed, but then it was pointed out to us that there are all sorts of funny kinds of information, and there's no possible justification of this. You know, how are we going to say that if some character comes up with a big machine and claims to be able to transmit information fast? Well, we can test him, but, you know, how are we going to show, without testing every conceivable means of transmitting information, how are we going to, and we don't know what they are yet, maybe some new ones will be discovered, how are we going to make this at all plausible? Well, when it's replaced by min, it becomes very plausible. Okay. So let me... Okay, so there's our father figure, looking very nice. Okay. So 1905 was Einstein's Annus Mirabilis. He wrote 4 or 5 very famous papers in that year, but I think the most famous one is this one, in which he showed that it was consistent for the speed of light to be a constant independent of the observer. Now, just for the moment, let's sort of think of that. Let's slow it down a little bit, and suppose the speed of light has got to be 5 miles an hour. So that's roughly walking speed. Somebody's walking away from me at 5 miles an hour. And then if I start walking this way, it seems they're walking relative to me at 6 miles an hour. Or if I started walking at 1 mile an hour this way, they would be walking only at 4 miles an hour. So it doesn't seem possible at first sight for the speed of light to be a constant independent of the observer. Suppose I run very fast after this light. Does it still go away from me? Well, yes, it does. And it's not easy to see how that can happen. And I'm going to present you with a very simple way of looking at relativity in which you see that that can actually happen. This Michelson-Morley experiment is very famous. The speed of light, light was supposed to be waves traveling in a rather curious medium called the ether. The available understanding of wave motion was that it had a uniform speed, constant speed with respect to the ether. And then, if that were true, now the Earth's moving around the Sun at quite a high speed, unless it perhaps dragged the ether along with it or something, there should be occasions when it's moving towards the light coming from some particular star, and other occasions when it's moving away. And so we have this little sort of thought experiment that I indicated with thinking of people walking away from me. We have it free, so to speak, except that the speeds are very much greater. And Michelson and Morley tried to detect this. And they just had absolutely zero result. And it's been done many, many times since then. Okay, well now let me say, I'm going to come on to, this is a sort of picture that should be familiar to a number of you. This is the way it's normally drawn. And what I'm going to say is I'm going to turn it through an angle before we do it. So the light cone is where light travels. If we're, say, at this point, this is space-time. We have space going horizontally. Sorry, I forget that you can't see my hand in front of this screen. At least I hope you can't. We have space going horizontally. Ooh! Oh, I must make sure I don't accidentally hit this thing. We have space going horizontally. This shows space as being two-dimensional and time going vertically. And light goes along this cone. Now, anything else travels slower than light, and so it can't get too far from the vertical. Okay, if we have something that's traveling at a more normal speed, then it's more or less, its track in space-time is nearly vertical. And okay, if it is indeed true that nothing can travel faster than light, then 2 points, say this point and some other point outside the cone, are sort of incommunicable. It's impossible for light to travel fast enough, or for anything else, according to the theory of relativity. Now, what I'm going to do, to get from one to the other, I'm sorry, I never finished that sentence. What I'm going to do is turn this picture through 45 degrees and reduce its dimension by 1. Okay. Oh my, can we see those diagonal lines there? I hope you can. Can you? Yes. Good. Okay. So now, the time direction is going to be this one here. If you're staying still, I mean, the guy whose position is indicated by these successive black dots is staying still. He's staying in the same point of space, which is in the other direction, and then time is increasing. Okay. These points, I promise not to use a formula, but I'm going to use one or two very simple formulae. This is the point 1, 1, and then the point 2, 2, and the point 3, 3. Those are the points on the diagonal. And those are the points at which his clock ticks. This person who's staying still, the still guy, his clock ticks as it crosses any one of these diagonal lines going downwards. So, okay, 1, 2. The unit, I'll sometimes think of it as a second, sometimes as a year, sometimes as an hour. It doesn't very much matter what the unit is. And here's the new picture. And the new picture is really rather different. This first curve here, these are hyperbola, and the equation of a hyperbola, rectangular hyperbola officially, the equation of a hyperbola is xy equals something. So the bottommost one that's drawn here, sorry, I must find some way of having enough space to do that. This bottommost hyperbola is xy equals 1. And that passes through the point x equals 1, y equals 1. And then the second hyperbola, here it is xy equals what? 4. Because it passes through the point x equals 2, y equals 2. And then xy equals 9 is the next one, and so on. And the reason, so it's xy equals t squared, where t is the time. And the reason why that is t squared is it goes through the same points as it did last time. Let me go back. There's the picture that we had last time. So all I'm going to do is say that we can imagine that this is the way clocks tick. That if you're traveling a straight line, every time you cross one of these hyperbolae, or that's the plural of hyperbola, your clock ticks. I just want you to sort of get clear that that's a possibility. And, okay. Now I'm going, so I refer to these, by the way, as the old picture, which is x plus y is a constant. And that constant is twice t plus t. That's the old picture. That's what the kind of universe we thought we lived in. And then the new picture is xy equals t times t. Is the universe, it's a closer approximation to the universe we actually do live in. Okay. Now let's look at what happens in the old picture. I should say, whenever this business about clocks ticking as you cross these curves is only if you're traveling at uniform speed. As long as you're traveling at uniform speed, then your clock ticks every time you pass one of these curves. Now, the old curves are just straight lines. The new curves are hyperbolas. What happens if you change speed? Well, this is a guy who is... I'm sorry. I must find a way of training myself not to click this thing. So here, this person changed speed. In fact, he was moving from left to right, and then he started moving from right to left, and also not quite at the same speed, but it doesn't matter. So now we set up a new coordinate system and a new system of curves. Whenever you change direction, it's conceivable that you'll move in a curved line. Well, I'm not going to suppose you do. I'm going to suppose you always move at a uniform speed, and then you can change that uniform speed every now and then. If you move in a curved line, you'd have to continuously change. It would be rather complicated. Now, you see, this thing doesn't make any difference here. These straight lines, the new straight lines here, in this corner up here, are the same as the old straight lines. You know, if I just continued the ones, from down here, they would actually be the same curves. And so, in the old picture, time is absolute. It doesn't matter how you're moving. You just click every time you pass one of these downward straight lines, which are uniformly spaced. Now let's see what happens when we... Oh, sorry, I'm moving backwards. I'm so unused to this. Okay, here's the new picture when we change speed. We went t equals 1, t equals 2, t equals 3, t equals 4, and then we just changed our speed instantly. And then we start with a new collection of hyperbolae along here. It's not perhaps so obvious immediately, but if I just continued this sequence of hyperbolae, they wouldn't be crossing at the same place. Okay? So now, when you change speed, your notion of time changes. Okay? Now that may seem a little bit peculiar. All I want you to sort of understand, and I'll come back to this time and time again until you're thoroughly bored with it, is that this picture is a possibility. It's consistent. If we were in control of this little 1 plus 1 dimensional, one dimension of space, one dimension of time. If we were in control of this universe, we could think, this person has crossed the nth hyperbola now. I'll make his clock tick. Okay? It is perfectly conceivable that a world could operate like this. The astonishing thing is that our world does seem very closely to operate in this strange manner. Okay. Some of you may have heard of the twin paradox. Have you? I mean, well, I see some yeses. So this is one of the sort of famous paradoxes of relativity. famous paradoxes of relativity theory. Namely, suppose we have two twins. I don't know who first invented it. Maybe Einstein, I don't know. And one of them stays at home. The other travels very fast, very nearly at the speed of light, towards a direction I'll call right. Right on these pictures is slanting downwards. And then he does that for a certain amount of time, and then he turns back and travels very fast in the speed of light back to where his stay-at-home twin was. His stay-at-home twin will be at the diagonal all the time. Right. Now I've made it, can we see what those things are? I've made him travel. This picture, by the way, is not to scale. So you'll find certain inconsistencies if you look at it in detail, but if I made it really to scale, this would be a very, very thin line indeed. So this man travels from 0, 0, which is where we started, to x equals 64, y equals 1. Okay, xy is then 64, which is 8 squared. Okay, so he's on the 8th hyperbola. Okay, so you can see these 8 hyperbolae stretching over that little rectangle. And then he turns round, and this time he increases, where is this thing? This time he increases x by 1 and y by 64. That's exactly the same sort of thing, except that he's interchanged x and y. And of course he's starting from here. This is in a way the new origin. And so he gets at 65, 65, but he only takes 8 years, the square root of 64, to do so. Okay, so the travelling twin ages by 8 years on each half of the journey. Okay, and now we come back and see what stay-at-home did. Well, this doesn't look very square. It's supposed to be square. Stay-at-home just stays at home, in other words, on the diagonal. But remember that we did get to 65, 65. So xy at the end of it is 65 squared. And so we're at the 65th hyperbola. We haven't bothered to draw them all. So the stay-at-home brother ages by 65 years. Okay, I don't think I've said enough, really. I mean, mathematicians, I hope, will find that a remarkably simple way of illustrating relativity theory. But I think the rest of us may be a little bit puzzled. What can I do to get rid of that puzzlement? Well, okay. We're talking about people who live in a one-dimensional space with a one-dimensional time, and all that's changed from our usual way of thinking about things, let me go back to one of these things. All that's changed from our usual way of thinking about things is that instead of the clock ticking every time the path passes through one of these downward sloping lines, we make it that the clock ticks every time we pass through a hyperbola. And if we change direction, we reset the whole curves. Okay? Do you see that we can actually make that happen? I mean, there's nothing inconceivable about that. We can equip each little person with a clock, you know, and we can advance those clocks in accordance with this simple rule. It's not the usual rule, but there's nothing you can say that's wrong with it. I mean, it may seem bizarre, but that might actually be the thing that happens. If we have consistency, that's the only thing we can really demand of a mathematical or physical theory. If it's consistent, then it might be what happened. What happens. You can't disprove what happens, because that would mean it was inconsistent. You could get some kind of contradiction. But you obviously can't get some kind of contradiction just by making people's clocks tick in this particular way. Okay. Well, now look at this. What I have here is, first of all, the original set of hyperbole, which is in this sort of region at the side. And then I've not shown you their tracks, but two people started off at the origin. One of them got to here, and one of them got to here. And then they're perhaps discussing changing their speed or something. I haven't actually said which speeds they're travelling from. But do you notice that these curves here, which show how their respective times increase, these curves cross each other. Now that's very important, because how can I say it? If we're, I can never see the cursor. Oh, there it is. Let's suppose we're in here. It disappears when I don't touch it for a time. And then if I touch it, it will advance the... I don't want that. Help me, yes, help me. First of all, I've got this set up, which I don't want. And then go back to the previous one, which we can go this way. Okay, now, I suppose I just have to keep this alive all the time. Okay, well, this is going to be very hard for me. But, you see, how can I say it? For this point, the bottom clock ticks number... I can't do it. I'm sorry. The bottom clock has ticked 3 clicks since we went, and the top clock has ticked 4. For this point, it's the other way around. Okay? And so, if indeed we equip people with watches that are ticking according to this new rule, then they will time events differently. One person can think that event A happened before event B, and the other person that event B happened before event A. So that's really important. It's not just that the time on somebody's clock may depend on who that somebody is and how fast they're travelling. It's the actual time order of events may be different. One person will think event A came before event B, and another person will think event B comes before event A. That's it. Sorry. So let me say, why that's a big deal. You see, suppose it were possible to travel faster than the speed of light. Then, from another point of view, from in another person's clock, you would be travelling backwards in time. You'd get you'd get somewhere, and you'd then get all the paradoxes of killing your own grandfather, that sort of thing. You get a definite contradiction to causality. If you could travel faster than the speed of light. It's not just that the speed of light has some magical property and that Einstein said you can't travel faster than the speed of light. What Einstein did was show that it was consistent to have this new way of timing things. In the new way of timing things, the speed of light is a constant, independent of the observer. I haven't bothered to prove that, to verify that, but it really is true. It doesn't matter if you're travelling horizontally along here, then it's the same speed, no matter who it is. And what else? But the important thing is this: all the laws of physics are invariant under this possible time change. Well, let's start to discuss that. Okay, so let me make it clear. This picture that I've introduced as a possibility is actually what happens in the real world, except that in the real world we have 3 dimensions of space and 1 of time. By the way, perhaps I should say this is for people who actually have met this sort of stuff before, but haven't met my particular way of explaining it before. In the standard formulation, one has x squared plus y squared plus z squared minus, well, one normally says c squared t squared, where c is the velocity of the speed of light, but I'm going to take that to be 1. And this here is, well, we would normally call that r squared in most textbooks, meaning the distance from the origin. I'm going to call it s squared minus t squared. And then this is s minus t, if I got this right, times s plus t. And these are my x and y. I change coordinates by taking space minus time to be x. Perhaps I'll go back and have one of those. Space minus time is x. Yes, space minus time is x and space plus time is y. Okay. Sorry. Okay. So let's look now. This is the old picture. And the yellow part is where it's a neighborhood of the diagonal, and that's where you must necessarily be if you don't move too fast. Okay? If you're moving in this horizontal direction, if you're moving in this horizontal direction here, then you're traveling at the speed of light towards the right. And if you move in the vertical direction, you're traveling at the speed of light towards the left. If you're staying in the diagonal direction, it means you're dead still. And if you're only going a few hundred miles an hour or something, you're very nearly still. So you're in this yellow region. That's what it means to be at low speed. And now that's what the old picture, that's the kind of world we thought we lived in. Okay? And here's the kind of world we do live in. Well, it's not very different. Okay? Let's move down a little bit. Here's the old world. Let me show you this is not very different. If you concentrate on what's in that yellow part, well, it's not very different. Okay? That's how we were deceived. If you don't move very fast compared to the speed of light, you can't tell the difference between the old picture and the new picture. And I should say that this thing very much exaggerates the effect. If you're traveling at, say, 1,000 miles an hour, okay, let's just think, 1,000 miles an hour, light travels at 186,000 miles a second. Take 186,000, then multiply it by the number of seconds in an hour, 3,600, and divide it by 1,000. Well, it's too complicated even for me. It's 186 times 3,600. It's quite large. And so this amount of slope here is very much smaller than I've indicated. Very, very much smaller. So it took a long time before anybody noticed that these two pictures weren't the same picture. Okay. Perhaps I should mention that the first people to notice, well, there's a little bit of a sort of prehistory to relativity. H.A. Lorentz found the equations before, quite a long time before Einstein. Michelson and Morley found this curious constancy of the speed of light empirically. They didn't imagine that it was actually constant. They tried to find other kinds of explanations. There were other people too, but Einstein was the first one who seems to have believed in it, who seems to have thought it's really real. You know, there's a thing called the Lorentz-Fitzgerald contraction, which says if things are travelling very fast with respect to the speed of light, they shrink in the direction they move. That's not true at all. They stay the same size. That's a way of trying to understand relativity based on non-relativistic ideas. There are all sorts of other things. Well, now, the really important thing is the notion of symmetry. So here, let me come on to the next picture here, and the one after that. If you add a constant to x, sorry, this is a sort of picture of a truck. It's not very detailed. If you add a constant to x and subtract the same constant from y, then this truck will just move down like that. xy has become x plus 4, y plus 4. What's preserved in here? Well, the value of x plus y is preserved. If I add 4 to x and subtract 4 from y, then x plus y is constant. And x plus y, remember, well, it's actually twice t. X plus y is t plus t. So this is what we're accustomed to, namely, if you are travelling at a uniform speed, and Galileo first noticed this, he described it in terms of travelling on a ship at a uniform speed, then, you know, if you do these things of throwing balls in the air and waiting for them to come down and so on, and you ignore the wind, which is probably likely to be more noticeable at sea, but never mind, then you get the same laws of physics. Nowadays, I think we normally think of it as travelling on trains. Maybe nowadays people think of travelling on trains. But if you let's do an experiment on a train. You know, we can roll marbles about, we can play marbles on the table of the train, and as long as it isn't actually jerking in some funny way, we'll observe the same physics as if we weren't moving at all. Okay. Well, now, the same principle is actually true in relativity theory, but it's a different symmetry that we take. So this time, the symmetry is to multiply x by a constant. Last time we added a constant to x, and divide y by the same constant. So here we are. Here is my same truck. I sort of didn't position it terribly well, I think. And now I click, xy becomes 2xy over 2. And this was actually drawn by doing precisely that operation to x and y, halving x. So you can see halving x would squash it vertically, and stretching y stretches it horizontally. Okay, now what's the point of that? Well, the point is that which is called Lorentzian symmetry, well, that's a particular Lorentzian symmetry, is very like Galilean symmetry. Mathematically, you're just multiplying rather than adding. It's very like Galilean symmetry, but it preserves the way our clocks tick in the real world, in the new world, shall we say, in which they tick when they cross hyperbolas. Because if you multiply this by this, if you multiply these two by each other, you get the same thing as if you multiply these two by each other. That advances me too far. Maybe I'll switch that off a little bit. So this is the way we overcome this defect that the axiom called Finn had. The other two axioms, remember, were operational. You can check them. Okay? Now, you can't check that there's no way of transmitting information faster than the speed of light. That's a sort of negative operation. So we have to do something else instead. And what we do is we check that all the laws of physics are invariant under Lorentzian transformation. That's the new kind of symmetry that the world has. Squashing and stretching by the same factor. So that has been done in the 100 years since, Einstein discovered the theory of special relativity. People have checked all sorts of laws of physics, and they've all been invariant. They've all had this symmetry property. Lorentzian invariance is a kind of symmetry. So the laws of physics have this symmetry property. Okay? And now we can see why it's impossible to travel faster than the speed of light. Because if you could travel faster than the speed of light, if you apply one of these Lorentzian symmetries, you could travel backwards in time. And then the law of causality, nobody's ever found anything wrong with that. You can't go back and change the past. It's just not on. Well, maybe you can. Maybe on very, very tiny scales you can change the past or something. No, but we're not going to talk about those. We're going to talk about experiments that we perform that are actually macroscopic in size. They're human-sized experiments, not particle-sized experiments. We might call them measuring spins of particles, but in the end, what we measure shows up as a spot on a screen. Okay? And if that spot on the screen has already happened, it's no good trying to change the past and make sure it doesn't happen. So this axiom fin really is true because of a symmetry property. That symmetry property you can check. You discover a new fact about physics, check it's relativistically invariant. And you see things like this in the Science Times every now and then. Somebody has done a new experiment which tests relativity in a new way. I will say what the axiom called min is later, but essentially it is that an observer well, no, I don't think I'll carry on and try to discuss that now. I'll save it till later. Now I'm going to come on to what is effectively this third axiom of ours called twin. And this is based on what's called EPR. And here's a little piece from the New York Times for May the 4th, 1935. And I don't know whether you can read it clearly enough. It says that with two colleagues, who are Dr. Boris Podolsky and Dr. Nathan Rosen, Professor Einstein has discovered something wrong with quantum mechanics. I'm not going to give you time enough to read all of this, but, well, maybe if you want to sort of read it, we can say it how. But I'm going to talk a little bit about what the experiment was. In the original form that was mentioned in the EPR paper, the EPR stands for Einstein, Podolsky and Rosen, they address this problem. How can I say it? You've got a particle here. It's got a position and it's also got momentum or speed. Let's suppose we know what the mass of the particle is. And this very celebrated principle of Werner Heisenberg's is, if you measure the position very precisely, there's no hope of measuring the speed precisely, or to be stricter, the momentum. And conversely, if you measure the momentum, there's no hope of getting the speed right. The way it's normally sort of explained in the popular books is that measuring one changes the other. Well, that's nonsense. What's more true, consider what happened in... we're going to replace these by spins. It's not true, when I said the 101 law, it's not true that measuring the spin in one direction changes what the spin in another direction is? The answer is, it's not consistent with the 101 law for the spins to exist before they're measured. And a very similar thing happens here in the Einstein-Podolsky-Rosen theory. It's not consistent for there to exist at one and the same time a precise value for the momentum and a precise value for the position. I'm going to proceed onwards. They say quite a lot. That was May the 4th, 1935. A few days later, here's a statement by Einstein. He was absolutely furious. Any information on which your article was based was given to you without my authority. Notice it says in your issue of May the 6th. It was actually in the issue of May the 4th. But anyway, so that's a certain inconsistency. But anyway, he was furious. It's generally believed that Podolsky is the person who let the cat out of the bag. But anyway, that's that. Okay, so let me say what happened. This is the famous paper that appeared later in 1935. I think it was November in 1935. Can this quantum mechanical description of physical reality be considered complete? Here is the idea of the EPR thing. There are various pairs of properties that are incompatible in the sense, well, as I say, it's usually explained as if you measure the act of measuring one disturbs the other. Well, we've seen that that's not, in the case of particle spins, that's not a correct description. Let's continue to use that incorrect description for a moment. So now, the idea is, prepare two particles somehow, and then separate them somehow until they're very, very far apart, so that light can't possibly travel from one to the other in between the times you're going to make the experiments. And you arrange that, well, the way we'll do it, we'll arrange that they give the same answers to the same questions. But what it really matters is you can measure property A on either particle, and it'll tell you what property A on the other one is by a law of nature or something. You can also measure property B on either particle, and it'll, for the same reason, it'll tell you what property B is on the other. And now the clever idea that EPR, Einstein, Podolsky, and Rosen produced, is separate these particles so that no influence can possibly travel from one to the other in the time you're going to make the experiment, and then measure property A on one particle and property B on the other. Isn't that clever? And then you appear to be able to know what property A is on each particle and what property B is on each particle. Well, I'll explain why that isn't sort of contradictory sometime, but so what are the properties that we might consider measuring? Well, EPR suggested that they should be position and momentum. If you take these particles and arrange for them to fly apart, they had total the total momentum 0, and so whatever the momentum of this one is the negative of the momentum of the other one. So if you measure the momentum of A, you've measured the momentum of B. But it's also true that the speed with which particle A went its way and the speed with which particle B went its way are the same, if they're the same type of particle anyway. So the velocities, if you like, are mutual negatives of each other. That means the speeds are the same. And therefore you can measure the speed of whichever particle you didn't measure the position of, measure the positions, they'll have got the same distance in the same time. So once you've measured the distance of one of them from where we started, you've measured the distance of the other. David Bohm, who wrote a very good textbook on atomic physics, suggested that that be changed to you're discussing spin-a-half particles, and the same sort of thing is more or less true. You bring them together, measure their total angular momentum, separate them, and then if they're spin-a-half particles, the spin of one is plus a half and the spin of the other is minus a half, and you can do that. For us, because we have to get the Cauchy-Specker paradox off the ground, we take spin 1 particles, and now perhaps you can see where I'm going. I don't know whether you can or not, actually. Maybe, sorry, let me just see. I think this is my last, yes it is. You can perhaps see where I'm going. What I'm going to do, the experiment we consider doing, is a twin version of the Cauchy-Specker paradox. Okay? And that will satisfy the requirement, I seem to have rubbed it out, that I put up in chalk, I think, on the board. Namely, well, let me just say it out loud. What was shown to be impossible by the Cauchy-Specker paradox is that there's a function just of direction which tells the particle what it's going to do. Or, that the particle is going to tell us what its spin is. Well, now the question is there perhaps a function with more variables in it? It depends not only on direction, but perhaps on the order in which you ask the questions, perhaps on the day of the week it is, whether there's a cosmic ray just whizzing by, the conversations of the experimenters, anything. So we're going to take all the information in the past history of the particle and say what it does cannot be determined from that entire history. It's not a function of the entire past history of the particle. I don't think anybody's ever said that before. I mean, there are plenty of physicists who believe our statement, but they believe it on too little evidence. They suppose that the state function, for instance, determines everything that can be determined about the particle. That's never been proved, And all sorts of people, including David Bohm, have toyed with ideas that what the particle does depends on some hidden variable, something inside it that we can't observe. But now it can't depend on any of those. It can't depend on the entire past history of the universe from the experiment. So the proof of that is what it'll be done by the end of next lecture. I think I'll stop there for now. I'll take it back to, say, here, so that anybody who just wants to read it while we're chatting on can do so, but I'll stop at that point. Thank you.